Okay. Now, your delta y, your change in the y coordinate of the point at which your force is being applied, is what? Well, final value y minus initial value y, but what are the two values of y? Well, let's look at the picture. Now, this is kind of a small picture, but it ought to be really obvious to you that, you have this vector, which is the vector at your initial theta, which in this case was 300 degrees, but it could be something different. And then you have your theta f, about 20 degrees past that, okay? Modeling this case, okay? That's kind of the way the picture looks for this situation. What's the change in y? Well, right here is your initial value of y, which is your vertical position, and right here is your final value of y. Okay, these are just the projections, because of course, don't even have to think of it as a projection. Everything on this level is at the same value of y, and of course this line goes through your initial point of application of the force. And this line, again, right along the, every point along this line is at the same y coordinate. If I drew it horizontally, of course hand drawn, it might not be quite horizontal, but that's the intent, and that should be obvious. So everything here is at the same y, which means this point is at the same y value as this point. Now, what about this point and this point? Well, these are the projections of these points onto the y-axis, which means that if this is a circle of radius 12 centimeters, this yf, this final y position, is 12 centimeters times the sine of theta f, and the initial position is 12 centimeters times the sine of theta naught. Now, the delta y vector is that difference multiplied by the j vector. Then, what's our change in potential energy? Everybody wants to use MGH. I'm telling you, get out of the habit. You will not be able to use it for most of the calculations that we do second semester, and some of the calculations that we're going to do in about a week about gravitation. Okay? It only applies in very limited conditions, and that's not the definition of potential energy. It's a formula that you can use with impunity if you know when and where it applies, but it is not a definition of potential energy, okay? It's just one formula used in one circumstance to calculate potential energy, okay? We define potential energy in this course in terms of changes in potential energy. And our definition is the change in potential energy is equal and opposite to the work done by the conservative forces that are acting on whatever is changing its position, okay? That's our definition. Nobody can repeat it. I've repeatedly, probably half a dozen times, made it very clear. We need to know this definition. I urge you to know this definition so you don't get confused later. I see people try to use MGH to calculate electrostatic potential energies, by doggone. If you had any idea how absurd that is, you would take time right now and make sure you understand this definition, okay? Okay, well, anyhow, there's our definition. And what work is being done by what is the conservative force here? You have to identify your conservative forces. Well, there's only one, that's gravity, acting downward, exerting a force of 0.05 newtons in the negative y direction, okay? So that force is negative, it's negative 0.05, or 0.05 newtons times negative j, because j vector is up, negative j vector is down, okay? So it's the equal and opposite to this. The work done by the conservative force is your negative 0.05 newtons times j, and then that's multiplied by your delta y. Well, Most of the class understands the dot product. There are some members of the class who don't. So all I'm saying is, okay, well, your delta y is going to be this times j. And of course, in this case, your theta naught is your 300 degrees. Your theta f is going to be about 320 degrees, within a couple of degrees. And you have to calculate that to get this more accurate. Okay, so you're going to have an expression for your delta y. Well, then, in this case, delta y is going to be positive because yf is greater than y naught. Waving hands a little bit, I said for right now, if you have a j here and a j here, or an I here and an I here, or two k's, they kind of go away. Now we'll define dot product and you'll see exactly why they go away. Just because the dot product of j with j is 1, or I with I, or k with k. Also, just for preview, the dot product of I, j, or k with any of the others is 0. Okay, well, here we have it then. If we multiply this by the delta y, the j's go, well, if we do this multiplication, your delta y vector is some multiple of j, and this is a multiple of j. So you just have this times your delta y. Okay? So you calculate your delta y, very easy to calculate, multiply it by all this stuff, and that's going to be equal and opposite to the change in kinetic energy by the work energy theorem. Okay? So if you don't understand that, look at the work energy theorem. Now we're assuming there are no dissipative forces. The work energy theorem says that the work done by non-conservative forces equals the change in kinetic energy plus the change in potential energy. So if the work done by non-conservative forces is 0, this plus this is 0, which means that these two are equal and opposite. One is the negative of the other. So that's why I say that the potential energy change should be equal to negative the change in kinetic energy. We calculated the approximate change in kinetic energy up here. Up here it's about negative 0.001 joule. That's a change in potential. That's a change in kinetic energy. So the change in potential energy is probably going to come out pretty close to 0.001 joule positive. Now remember, this is only an estimate. So the number that you get here is going to be a little different than the number you get here, but it's going to be fairly close. I think within, maybe within 10%. I think kind of probably within 10%, but certainly within 15%, unless I'm totally off the wall here, which is entirely possible. Okay, well, those are all important calculations that illuminate all kinds of things: conservation of energy, angular velocities, angular accelerations, angular quantities, and the vector form of the angular quantities, the directions of your angular quantities, and relate everything to the work energy theorem. So I really kind of like this example, okay? So I really want you to understand this very thoroughly.